At the outset, I extend a very warm welcome to the galaxy of esteemed guests that are there with us. Professor Prabhat Ranjan, who has consented to be the chief guest of this valedictory session, on members of the editorial and advisory board of our journal, Vantage, Journal of Thematic Analysis, under the aegis of which this international conference has been organized. So on the behalf of Methray College, I extend a very warm welcome to you all. And I thank you all for accepting our invite and being a part of this. And I also take this opportunity to welcome all our delegates who have joined from different corners of the world and all the members of the organizing committee who are there and who all have been working for the past so many days to make this conference a reality and a big success. And I was going through the messages that were being posted in the chat box just 2 to 5 minutes before, wherein everybody was just wondering that why is this slideshow being going on? And as we all know that it's a moment of pride for Indians that we are celebrating the 75th year of independence. In fact, it is culminating, and from 15th of August, we'll be stepping into the 76th year. And so many celebrations are going around not only in India, but even in different corners of the world, because India being the largest democracy, everybody is keeping an eye that the how we would be celebrating this event. And the people who are part of Delhi University, they are already aware, but for others who have joined from other universities, I would wish to share with you all that it is indeed a very important year for the upcoming year is very important for the students or the alumni of Delhi University, because our alma mater has completed a century of its existence. So Delhi University has a glorious past of 100 years now. And when then so many things are happening at the same time, so it becomes very pertinent to understand that what would be our vision for tomorrow and how we have obtained what has happened over the past. So this is the time, and when we think of any academic institution, when we have to celebrate, the celebration is always in terms of organizing a program, organizing an event where we can have constructive deliberations, where we are able to engage eminent people across the globe at one platform, and we come up with something different. Maybe the things, because whatever is being discussed here, it has now, it maybe it will become a history, and so many things would be added to the global pool of knowledge. And when these things are happening, it is very important for us to understand what happened and how did we arrive at this present day. And when we look at this particular exhibition, this was the virtual exhibition which has been made by the UGC, University Grant as a Commission. And this particular, because if you look at it, it comprises of so many pictures, pictorials are there, some newspaper clippings are there. So it is simply a reflection that how this information has been stored. This information is there with us, but we have never used, we never realized. And maybe we always talk about what are our rights, what should be our responsibilities. Many times we don't even think of those things. So we thought that at this valedictory session, when this is being attended by our students also, it is our responsibility to make our youth understand that the freedom that we have with us at this stage is because of the sufferings beyond. This is the foundation of which is being laid on the sufferings of so many people. And those people are no one but our grandfathers, great grandfathers, mothers. So we should acknowledge them. And I was listening to the deliberations which were going on in the previous session. And I was thinking that maybe this is the very apt thing that has happened. And this is very much in sync with the theme of this conference also. So I was saying that when we thought of celebrating these glorious moments, we thought that we should have some conference, and this equinox, that is why it was organized towards the completion of 75 years. And we select, that is why it was the main reason for choosing these three dates, 11th, 12th, and 13th of August. And though it was a festival time, on 11th it was Raksha Bandhan, but still everyone was involved, because we thought that this is our best tribute this is the best tribute of any academician, and this is what we have done. And when we talk about, because during these 3 days the deliberations that were on, we talked about every aspect was taken into consideration, whether it was public health, whether it was understanding nature, it was understanding that how we can, what is happening around us. But the purpose is that, or when we were talking about the tribes, because they themselves, they are, because they have been able to survive themselves over such a long period, from generation. I think they are the best examples of what we are, when we talk about sustainability. So maybe there is a lot that we need to learn from them. Many times nowadays, as it was just being discussed, that we have to make them a part of a mainstream. But when we talk about mainstream, maybe it is not a unidirectional, it is bi-directional. We need to learn a lot from them, that how, what do we mean by sustainability when we talk about agriculture, what is sustainable agriculture. These are the things which we have been talking about very often nowadays, but maybe these are the things which we need to learn from our ancestors, from the way they were practicing it in past and the way even the tribes are practicing today. So we have to be everything, we have to bring them. When we are saying that everyone should be at the same platform, so it does not mean that they have to go, they have to climb up the ladder. Maybe we also have to put a foot down and understand that what are the common things between us, and only then we can have a society which is more sustainable. And in one of the sessions, the major emphasis was, when we talk about preserving our nature, it is not that we are doing it for the nature, we are actually doing it for ourselves. It is our existence, our survival, which is under question. So that is why, when so many things are there, so we thought that maybe one under one umbrella which binds them together is the expanding frontiers of knowledge. And that is why this conference was given this particular theme, and we got large number of abstracts, presentations, and we are very happy to share that through these platforms we are giving the opportunity to the students, not only to the researchers or the faculty members, but even the students at undergraduate level. They are making their presentations. When we are talking about presentations, it does not mean that we want everyone to be a researcher. But when they are talking, when they're presenting their work, indirectly they are working on their soft skills. And this is the requirement wherever they may go. When they have to be part of the society, these are the small things which they need to understand. And moreover, when while working on the presentations, they have done so many deliberations, maybe lots of discussions. They were reading the text, they were going through different journal papers, they were reading, they were trying to understand and to get the thing around it. So maybe it has helped in building on their analytical skills, critical thinking. And these are the attributes which are required by every individual. These are not the things which are only expected of a researcher. This is what we want from everyone. And that is why, when we are organizing these at undergraduate level and offering an opportunity to the students, I think the teacher, the faculty members, the organizing committee of this particular conference, they have done a mammoth task, I must say, because this is not a small thing. And with 400 registrations, with more than 56 abstracts and so many paper presentations and about 8 sessions, I think it was for 3 years, it was a complete energy capsule, which has given us so much of food for our thought, and accordingly we will be able to maybe set our guidelines, or maybe we can set our vision for the upcoming 25 years. And this is what it has been very often talked about. And when we had in the inaugural session, which was where the vice chancellor of the university was there with us, Professor Yogesh Singh ji, and he was very appreciative about the sub themes of this conference, because he mentioned in his speech also that I'm so happy that every aspect has been taken well into consideration, and at the same time he said that all these sub themes are themes in themselves. So maybe he was saying that in times to come, I expect that the college would be organizing these conferences on these sub themes as well. So I'm sure that this is not the end, this is just the beginning. And every year we will be coming up with something different, something new, where we would be able to engage the global community, where everybody is there to share, interact, and this information, this knowledge which is being acquired here is transferred to our youth, to our to the youth who are actually, who are the future of this country, of the globe, not only this country but the entire globe. And we will make, we will have a life which is more sustainable. And maybe there are so many things that can be talked about, but I think this is the time when I should stop. And I request our other participants, and we all would be very eager to hear from our chief guest, Professor Prabhat Ranjan ji. And I once again extend a very warm welcome to him, and I thank all the members of the editorial board, all the members of the advisory board, and the managing editors, the organizing committee, for organizing this conference and making it a big success. Thank you so much. Thank you, Patil.
Thank you so much, ma'am, for capturing the essence of conference so beautifully and sharing the vision for Equinox with all its benefit. Thank you once again. We all know that Professor Prabhat Ranjan sir is invited speaker for this session. We are obliged, sir, that you have accepted our request to be the guest of honor in the valedictory session. Professor Prabhat Ranjan is the founder and Vice Chancellor of D.Y. Patil International University, Akurdi, Pune. He is a nuclear fusion scientist, a futurist, an educator, an innovator, and a science communicator. He did his college from IIT Kharagpur and obtained his PhD degree from the University of California, Berkeley. His remarkable scientific contribution, India's moon mission, wildlife, and agriculture sector. He is particularly known for his innovation in the field of assistive technology that has helped to put smiles on the faces of persons with severe disability. He is among the pioneers in India on using brain-computer interface to help persons in logged in and other condition to communicate. He has been nominated by Bureau of Indian Standards to represent India at International Standard Organization for BCI standardization process. Professor Ranjan has wide administrative experience. He has been executive director at India's technology think tank, TIFAC, Technology Information Forecasting and Assessment Council, and chairperson of National Steering Committee of AICTE Idea Lab scheme. He also created a flexible and futuristic multiracial BTech program in 2019, which has impacted computer science curriculum across the country in last 3 years. Sir has been a recipient of many awards at the national and international level, including National Science Talent Award, IBM Innovation Grant Award, Bihar Gaurav Samman, and most recently, EduStar, India's most impactful Vice Chancellor Award 2021-20. I invite Sir to deliver his talk titled Nuclear Fusion Dream Source of Energy. This talk would cover basic details of how scientists are trying to realize the dream of nuclear fusion and their status. Over to you, sir.
Thank you. Let's see. Yeah, can you see my screen, please?
Yes, sir. Yes, sir. It's visible.
Thank you. As very little running late, I would move a little fast. Thanks to the organizer for inviting me. Many of things that I've referred to in the document is mentioned in detail in my blog. I mentioned the blog site as ranjan.in at the bottom of the slide here. Before I proceed, I would also like to mention that as head of India's technology think tank, I was responsible for preparing a vision document for the country called Technology Vision 2035. Prime Minister wrote the foreword to this document. He launched it in 2016 at Indian Science Congress and asked all ministries and government departments to follow this document. As we are trying to work towards a vision for the next 25 years, it's important to understand this document. I don't have time today to talk about it, but many things that are happening in the country are happening because of what was done in this document. And one of the things that we had talked about in the document was about nuclear fusion. I'm the first PhD from India in nuclear fusion, which I completed in 1986. As was mentioned in my introduction, I was at IIT Kharagpur and also part of Delhi University. In fact, I was master's student at Delhi University before I went to Berkeley, where I was from 1981 to 86, where I did my PhD in nuclear fusion. I came back to India and joined Saha Institute of Nuclear Physics. For 9 years I was there, and the Institute for Plasma Research, Gandhinagar, where about 7 years I spent. And then I moved to Dhirubhai Amman Institute of ICT in Gandhinagar, where I was professor for 11 years. There also I worked on some aspects of nuclear fusion program. And in Delhi, for 5 years that I was there, I was talking about nuclear fusion as part of national policy documents and media as to what changes are happening in nuclear fusion domain and what we should do. And today, as a researcher, I'm the chief mentor of a project called Project Sunland in my university, which is funded by Silicon Valley. I will briefly mention about this also in the document. Those of you who are monitoring media related to this, there are a lot of news that keeps coming. This is, of course, more than a year old, which said China achieves China's artificial sun sets world record, achieves plasma temperature of 120 million. And also it's mentioned that 160 million for 20 seconds. In fact, 180 million has been achieved already by China. Just to compare that to temperature of the core of the sun, the maximum temperature of the core of the sun is about 15 million, about 1.5 crore degrees centigrade. So about 12 times of that of the temperature of the sun has been already achieved on Earth. Similarly, there are other methods of achieving nuclear fusion. There's a news item where National Ignition Facility in US achieves breakthrough in laser fusion. There's another news here. Commonwealth fusion system creates viable path to commercial fusion power with the world's strongest magnet. This Commonwealth fusion systems has been set up by MIT in US to realize commercially the nuclear fusion. So all this is the background, and those who are monitoring this news, it's happening regularly. Every few days, you see a new news coming up. The outline of this talk is that I will briefly describe what is nuclear fusion in case some of you are not aware. I will specifically mention about a particular device called tokamak, and I'll focus on what is happening in nuclear fusion domain in India. What is the international progress in this domain? What are the private efforts going on? And maybe touch about inertial confinement on another way of achieving nuclear fusion, and then conclude. So briefly, if we say that what is the aim of nuclear fusion, what we are trying to do is to capture sun and put it into a box. And as per one of the researchers, he said that the idea is great. The problem is we do not know how to build that box. We are trying to capture sun and bring it to Earth. A very interesting thing is that 1920, about more than 100 years ago, Dr. Meghnath Saha, who set up Saha Institute of Nuclear Physics, he gave a equation called Saha-Anderson equation. Some of you might have studied about this. This is considered to be the start of plasma physics. And when we try to achieve nuclear fusion, actually we try to create plasma, the fourth state of matter, as roughly we call it. And also in the same year, Arthur Eddington said that nuclear fusion is the process through which stars and sun gets its energy. In 1932, nuclear fusion in lab was demonstrated. And then since 1955, work on controlled fusion has been going on. Controlled nuclear fusion means that it should not explode. Like hydrogen bomb also uses nuclear fusion, but it's uncontrolled release of energy. What we have been working is controlled release of nuclear fusion energy. And from the time that we have started working, we have been always telling that it's about 20 years away. The time has changed, the 20 years has remained. But we believe that now that 20 years is coming down, and maybe another 15 years time, we should be able to achieve, if not earlier, the commercial use of nuclear fusion. So just in case those of you are not aware, what is the nuclear fusion? Fusion is the process of light atoms uniting to form heavier atoms, in which process it releases energy. All of you are also aware of nuclear fission process. In that process also energy release, and nuclear fusion also energy release. How is it possible that one case when you break the nuclei, you get energy, in other case when you combine the nuclei, you get energy? So actually iron is the most stable element. So higher atomic weight compared to iron, when you break the nuclei, you get energy, and lower than that, the lighter elements, when you combine the nuclei, you get energy. So inside the sun, as you might be aware, that it's the hydrogen and hydrogen reaction that takes place to produce energy. But when we look at the atomic power stations which use fission, it's the heavier elements like uranium that is used. Now, these nuclei are positively charged, so normally if you try to bring them together, they actually repel each other. You need very, very high energy to actually overcome this repulsive force. And obviously, it's not very easy to do this. So normally what is done inside the sun is the hydrogen-hydrogen reaction, but that reaction rate is much slower and not so useful on the Earth. So we are trying to use, one of the possibilities is taking isotopes of hydrogen like deuterium and tritium, and either using deuterium reaction or deuterium-tritium reactions, and those cross-sections are much larger. The deuterium-tritium cross-section is higher and it requires lower temperature, so deuterium and tritium reaction is a candidate for early stage of fusion reactors. But as we progress, we might have other possibilities, which I'll mention later on. But what are the problems that we face in this? One is creating this high temperature of 100 to 200 million degree centigrades, like 10 to 20 crore degrees centigrade. But as I mentioned, that's already been achieved. But of course, you need to keep it for a very long time. We have been able to achieve it for a few tenths of seconds. Second, the tritium is radioactive, although half-life is much smaller compared to many other radioactive waste that comes out of atomic power stations, which have hundreds of thousands of years of half-life. But tritium is also not easily accessible and must be bred from lithium. So these are the problems that we need to solve. And I will mention briefly how these are being done. So the deuterium tritium that we are talking about, when we bring them together at these high temperatures, and they combine together to produce neutrons carrying energy 14.1 MeV, and also they produce helium. Helium is like an ash, and this neutron that comes out, we capture the energy of neutron, and through the lithium blanket, and when neutrons bombard lithium, there's also a reaction that takes place, and tritium is produced. So you consume tritium, and then you produce tritium. So tritium is recycled through this process. And what comes out is basically helium and energy. Just to give a comparison of how does it compare with other sources of energy or the other ways of producing energy. For example, if I take 10,000 tons of coal, and the amount of energy that is produced in that is the same amount of energy I can produce through 800 grams of deuterium and tritium. 10,000 tons of coal, compare that with 800 grams of deuterium and tritium. Now, where do we get deuterium? Deuterium is contained in water, for example, very small percentage of that in water. You must be knowing about heavy waters. And tritium, as I mentioned, must be generated in situ inside the reactor. So we need initial tritium to start the reaction, and then later on it's getting produced inside the system. Just to give you another comparison, if I take one bathtub of water and combine that with lithium in a laptop battery, lithium in the laptop battery with that of the water that is in one bath of water, one can get energy for 50 years which can suffice the power needs for an average family. There's something called Lawson criteria, but I'll leave out the details. This text talks about certain parameters that must be satisfied for useful use of nuclear fusion. And okay, let me skip this. In my blog, I mentioned one of the blog is how I got into nuclear fusion research. Please don't pay attention to my hair there because now I've lost most of it. There's another blog where I talked about my contribution to nuclear fusion technology, and this has many links to other blogs that I've written about how various parts of nuclear fusion have contributed to. If you look at nuclear fusion, there are so many different approaches. If you look into this, there are too many to talk about. But if you look on the right side, there's one which is under the thermal category, where there's a magnetic confinement, there's an inertial confinement. These are the two main that one would focus on, and I'm going to focus more on magnetic confinement. So if I look at this curve, this slide, there is a gravitational confinement that happens inside the sun and stars. Okay. Where due to huge mass of these sun and stars, that confines the plasma and the related matters into a localized space. The inertial confinement is a method that is used that uses laser, and I'm not going to talk about that. I'm going to focus on magnetic confinement technology. Okay. So as we said that to produce nuclear fusion, you need to have 10 to 20 crore degrees centigrade. The question is that what is the utensil, what is the vessel in which you can keep it? Because anything that you keep in would actually simply be destroyed. So what we try to do is to create a magnetic field cage. And magnetic field, as you know, that if there's a charged particle moving, the magnetic field influences motion. And we use that magnetic field to actually confine the plasma into a cage, in the form of a cage. We create a cage, magnetic cage, inside we confine the plasma. There are two general ways that efforts have been made. One is called the linear confinement, which is shown here as magnetic mirror. And there are toroidal devices. For example, one of the main popular version of this toroidal version is called tokamak. And there is another version called accelerator. Personally, when I was doing my PhD work, which I finished about 36 years ago, I had combined magnetic mirrors and accelerators into a triangular shape, three-dimensional triangular shape. But then most of the world has been working on tokamak, and India also we are working on tokamak. So this is actually showing basic magnetic mirror linear device, which creates a magnetic field, which the charged particles follow the magnetic field lines and they get reflected back and forth. But of course, all of them do not get reflected. Some of them also get lost depending on the angle at which they're approaching the ends. Again, I'm not going to technical details of these. These are the toroidal systems where actually the losses that happen to magnetic mirror in the end side, you actually fold the thing back into a torus, and then the charged particles keep rotating inside. Of course, there are losses that happen due to other regions. And so we need to twist the magnetic field lines in a very complex configuration that would not be easy to cover in this session. But you can just have a look at the figures. The left side is the tokamak device that is right now the most popular, and the right side is the accelerator device. Tokamak has made the main progress. The reports that we have seen from China coming is all based on tokamak device, which is Russian abbreviation for toroidal magnetic chamber. On the right side, accelerator device. Accelerator actually was very popular at some stage till tokamak came in, but recently there has been progress in accelerators, especially in Germany. This is the cover page on PhD thesis, which combined the accelerators and magnetic mirrors combined together into what I call helically linked mirror arrangement, and I had named the device as Thelma. Again, I'm not going to technical details, but in addition to confining the plasma, we need to heat the plasma. There are two ways that it is done. One is through use of what is called neutral beam injection heating. Other is called radio frequency heating. These are the two main heating techniques that are used. These are supplementary heating to heat up the plasma to very high temperatures. In India, there were two devices built. One is the Aditya tokamak that was built at Institute of Plasma Research, Gandhinagar. Institute of Plasma Research, Gandhinagar is the main nuclear fusion center for the country, and another one, Saha Institute of Nuclear Physics, SINP tokamak, that was built in 1987. So 1987, SINP tokamak was actually built by Toshiba of Japan. It was a small device. You can see this photograph on the left side, upper one, and the bottom left one is the Aditya device, which was a little bigger one. I had the opportunity to work at both of these places. I will describe a little bit about this, but Aditya was a much bigger device compared to the SINP, although it was set up in 1989 and the SINP one was set up in 1987. Right now, not much work is going on at Science Institute of Nuclear Physics. That program is mostly stopped. So the Institute of Plasma Research is the main center where work is going on. And they also represent an international effort that is going. So this is the machine that was set up at Science Institute of Nuclear Physics. And I was a physics person who was into computer simulation. But actually, I got into experiments and various things. I'm not going to go into details of these. So I focused on problem. I learned techniques and developed experimental systems to make sure the reactor starts to work. Sometime around 89, 19, about 2 to 3 years time, I could get this machine to work. And I kept adding more facilities to this, including power supply and other things, which were very expensive to buy at that time. There's another blog as to how I got into a data acquisition system that I developed. This is about how I became an accidental experimentalist, because I was a simulation person. And then I was invited to come to Gandhinagar. And in 89, this machine started to work, but it's not working properly. 95, when I came, in about 5 days' time, I could get it to work. So we did many things. I was there for 7 years. I was also made project leader of this reactor. And so with both of these, the machine in Calcutta and Gandhinagar, I had the unique privilege of bringing the performance of both these machines to international standards. I also designed the control system of the new superconducting machine that was being built, which is being actually followed in ITER international project that is being done by contribution of all the countries. So this is a blog that describes what I did in the Aditya tokamak to bring the machine to higher level of performance in about 5 days' time. This is showing how I learned from rural technology and helped the fusion reactor. This is another blog which shows that a small photograph helped me bring the machine from death. This is talking about a mystery of error fields in the machine. There's a blog which talks about dancing sparks. It was kind of a spark in the air that we were seeing and how we solved that problem. This was an accident that happened and how we recovered from then. What was the reason for that? These are all blogs that I've written. And then recently, the Aditya machine has been upgraded after about working for 25 years into Aditya upgrade, Aditya U. And this started operation in sometime in January 2017. The now performance is much better compared to the earlier version, and the new facilities have been also added to this. In mid-90s, when we were preparing to build the superconducting machine, the SST-1 tokamak, steady state superconducting tokamak, this one at the bottom. At the same time, another 3 devices were being built in Asia, all Asian countries, Japan, China, Korea, and India. So not Europe or US. All this was happening in Asia. And actually, the Japanese had a much ambitious plan, which is the one that is on the right-hand side, this particular one. But this one is the Chinese one, and this is the Korean one. If I forget the Japanese part, and if I compare the 3 machines in China and in Korea and India, there's a comparison that I'd like to show. This is the SST-1 machine that was built in Gandhinagar. First time it was assembled in 2005. Then there were technical problems. It was disassembled and reassembled after about 8 years in 2013. And if I compare the 3 machines, then what you would notice that the SST-1, this is the one in India, in Gandhinagar. The East is in China, and K-Star is in Korea. All of these were built around the same time with not too much difference. But if you look at the performances, China, as I mentioned, the temperatures they have achieved is much beyond what they had planned. Korea achieved 100 million. India, we planned for about 10 million, but to the best of my knowledge, we have not gone beyond 2 million. In India, we planned to achieve 1,000 seconds of discharge. We have not crossed even 1 second, whereas the other ones have proceeded much more. And recently, even in UK, there's a private company that has come up that has shown about 100 million degree temperature. Unfortunately, India hasn't made good progress since last 15 years or so. What has happened in the meantime is that there have been a lot of technological advancements in few areas, especially high temperature, high magnetic field superconductors, advanced manufacturing such as additive manufacturing. Fortunately, I'm chairman of AICT committee to set up these across the country. And we have set up these facilities in Fab Lab across in my university. And then AICT requested me to chair a committee. Through this, we have set up this across countries. And today is very important even for physics people to have these facilities. Also, extreme high power supercomputing modeling systems, also artificial intelligence algorithms. All of these are helping us today to realize the dream of nuclear fusion. And due to this, investments in privately funded fusion ventures has grown tremendously. I'll just show you an example. The one on the top is the project that I'm involved right now. I'll talk a little bit more about this. But you look at Commonwealth Fusion System, in fact, this figure is outdated right now. It's already more than, I think, $1.5 billion that's been invested. Another one, the one at the bottom, I think Helion Energy has also got $1.8 billion and so on. So a lot of funding is coming into private industry through investors. In our case, the project Sunland that I'm going to talk about a little bit, this we had investment about $1 million promised by investor from US. Unfortunately, due to certain situation, the funding has stopped for the time being. But I'm going to talk briefly about what we are trying to do. I've called the name project Sunland because Sunland stands for fusion in Sanskrit. Nuclear fusion, we call it Navikiya Sunland. The first private initiative of this kind in India. In fact, only initiative among any university because there's only one center in the whole country that is in Gandhinagar. Outside that, this is the only other effort that is going on. I'm the chief mentor of this project. We are trying to develop nuclear fusion technology at 115 to 128 the cost of what is needed to develop similar in Western countries. While our target has been to produce energy, what we are trying to do is to use it as a neutron source or neutron factory in the early stage. So what we are trying to produce right now is a volume neutron source and use that neutron for three purposes. One is produce medical isotope. Second is to breed fissile fuel, that is convert thorium into uranium. And third one is to process radioactive waste of nuclear power stations. But of course, our long-term goal remains energy. Just to give a little bit more details on this, the medical isotope they're talking about, there's a particular medical isotope called technetium-99m. Technetium-99m actually is used for 85% of world's medical isotope requirement. And in US uses half of the world's requirement, but does not produce anything. There are about 6 fission reactors being used today to produce these medical isotopes. 5 of them are going to close in the next 8 to 10 years. There's one company in the US which is trying to do this through other methods, but right now not yet commercialized. So this is a huge shortage that we expect to see. And even today, the supply is not sufficient to meet the requirements. We did a calculation. We found that it costs about $3 billion to set up such a system. But the very first year, we'll get about $5 billion in return. So you put in $3 billion, very first you get $5 billion. Then every year you keep getting $5 billion. The second one, breeding fissile fuel. As you are aware, India has the largest reserve of thorium, 25 to 30% of the world's reserve is in India. There was a news item about 8-9 years ago, which said that the monazite sand that is in Kerala region, which contains thorium, there was theft of that sand, and that theft was equivalent to 60 lakh crore rupees. 60 lakh crore rupees. So if I can convert thorium to uranium using this nuclear fusion process, according to one collaborator from US, he said that it will be like Saudi Arabia discovering oil wealth. That's the kind of wealth it will produce for the country. Similarly, the last one, the processing radioactive waste, nobody has a solution to producing processing radioactive waste. We dump it with half-life of 200,000 to 300,000 years. And actually, we believe that we have a solution for this also. This is the Commonwealth Fusion System set up by MIT group. This is trying to, has already successfully reported high temperature superconducting magnets that they want to do about by 2022. So they've successfully done that. Now they are moving into the next phase of preparing a machine, which they've called a Spark. And that is the smallest possible machine that they want to demonstrate. And the next one will be the one which will demonstrate commercial level of production. Will cost about $2 billion to set up. So this is the Commonwealth Fusion System. Another company, Lockheed Martin, which had claimed something about 6-8 years ago, but they had not been successful. This is the escalator in Germany that has been showing good progress. This is the initial confinement method where actually you are using laser beams to hit the DT pallets from all sides. There have been some good progress in this also. This is the National Ignition Facility in US where they have demonstrated break even. That means the amount of energy you're putting in is the amount of energy you're getting out of the system. I'll leave out these. There's another method of using proton-boron reaction, which does not produce neutrons, but this requires about 2 billion degree temperature. But there are some other methods that are being used. Some companies are also attempting this, one in Australia and one in US, which does not involve any nuclear waste at all. This is called aneutronic fusion. This is being done by a company near Los Angeles called TAE Technologies. They have been helped by AI-based algorithm of Google, which has led to seeing them a great improvement. This is talking about news item about how nuclear fusion is revolutionizing medical isotope. They're talking about this is a Phoenix Nuclear in US, which is trying to produce this. Fusion can also be used to propel space systems, so you can reach out to deeper space. So this is also useful from a space point of view. Various governments are coming up with ambitious plan to promote nuclear fusion, for example, UK, US, and so on. India, I'm trying to get government's attention. And some of you are closer to power in Delhi. You maybe help me with this, is to get Indian government to actually differentiate between nuclear fission and nuclear fusion. Today, most of the policies are based on nuclear fission. So concluding the talk here, the nuclear fusion has been making headlines in recent couple of years, showing that it's close to realization. So the 20 years that we have been talking about is probably now come down to maybe 15 or so, or 12, 13 years. We expect that by 2035, we see the commercial realization of nuclear fusion. Private investment has been growing around the globe in spite of uncertainties and cost of developing nuclear fusion technologies. And I was personally surprised when I got a request from US to start working in India. With 4 decades of experience, India should be able to develop this technology at a much lower cost, just like we did in IT sector. We could do this with proper partnership. So it is a momentous occasion for private initiative in a challenging area like nuclear fusion in India, and governments must come out with clear policy and incentive to promote nuclear fusion industry in India. So let's stop at this point. Thank you very much for giving this opportunity.
Thank you, sir, for your informative and interesting talk. Research in physics encompasses tiniest length scale to scales which are astronomical, like the sun, which is studied both in astrophysics and nuclear physics. Indeed, nuclear fusion is going to be the next generation source of energy and will place India on the world map. Rightly said, sir, we have challenges, but in spite of that, we have been able to achieve, continuously strive for achieving more, and with all the diligent efforts, we are going to succeed. Session is now open for interaction. Please raise your hand if you have any questions, sir.
There is a question here, compared to nuclear fusion, how efficient is nuclear fission as a source of energy? If I compare these two, the nuclear fission still has many issues that I talked about, that is waste disposal and chances of uncontrolled release. We have seen accidents happening in all parts of the world, whether it was in 3 Mile Island in US or in Russia or in Japan. Whereas nuclear fusion is very safe. It does not require, it requires very simple things like water and soil. So it does not require any very difficult to get materials, raw materials. And as I mentioned that one of the focus that I'm trying to focus on is how to use fusion and fission in a combined way. That is using fusion to produce fissile fuel for fission reactors and provide that in the early stage. And then later on, you go to complete process of using fusion as energy. So that's what I'm talking about. There is a question about rural technology use. You can read my blog. I had seen my village, how when hand pumps were being installed, how they were doing it. I used that to solve a major problem of nuclear fusion, so that you can read in my blog. It says, sir, in the beginning, you said that there's some control ways of doing nuclear fusion. Can you explain how it can be performed? What does it mean by control nuclear fusion? Control nuclear fusion means that if you look at hydrogen bomb is uncontrolled release of energy. That means you can use for destructive purpose, but when you want to produce for peaceful purposes, you need to control the nuclear fusion reaction. And that's where our effort has been going for the last 70 years, is to confine the plasma into a volume using magnetic field. That's one of the methods. There are other methods. Using magnetic cage to confine this and produce very, very high temperatures, produce reaction, extract that energy out of this. This is what's called controlled nuclear fusion. What percentage of energy is coming out of nuclear fusion for accommodating the demand? Right now, nuclear fusion is not being used for any commercial purposes. We have not yet produced any commercial reactors, so there's 0%. But it is expected that if things go well, there are 3 scenarios. It was earlier expected by 2060 we'll have commercial use of nuclear fusion. But today I'm changing this to 2035, if not earlier. And so by 2045, we expect that 30 to 40% of energy will be produced through nuclear fusion process. But today this is 0%. So you mentioned that magnetic mirror and splitter were combined. Can we also combine with tokamak and a better result be achieved? Well, my PhD work was combining magnetic mirror and splitters. Can we also combine with tokamaks? Of course, each of these have used their own learning from each other. You can do a research work if some of you are doing PhD as to how you can take advantage of all of these together. When I was doing PhD, I used to actually talk about bad things of tokamak. And I used to say that, okay, magnetic mirrors are good, accelerators are good, and I can combine them. But then later on, I started working on tokamak as I came back to India. So one has to learn from each of these. And there's a question about what you did to bring Aditya tokamak back to work in just 5 days. I think you read my blog, please. I've talked about this there in detail. But 1989, it was made functional, performance very poor. 95, when I came to Gandhinagar, I was requested to look into what was happening because they had tried to get experts from all over the world to help it out. But then when I got a chance to work on it, in about 5 days, from Monday to Friday, I could get it to work. And then I was made project leader of that reactor. It's given in my blog. Thank you. Any other questions?
Urvashi?
Sir,
yes, sir.
the way the
First of all-
questions are, maybe just a minute, I would like to say something here. This was indeed very, I will not say interesting, but it was mind-blowing. We were so feeling when you were delivering the talk, it was giving a sense of pride also that in India, so many things are happening. And so India might become a leader in the technology in times to come. The way things have been happening and the way the questions are pouring, I'm sure, sir, many of the students, they might like to be your student only and work under you, because for whatever you have said, you have spoken, they were listening to everything. And that is why the questions are so specific to your talk, that what did you do in the 5 days, or whatever has happened, whatever was being talked about has been listened very carefully. So this is actually indeed the main role of holding such a conference, where we can engage our researchers, our students, because they are the future. And if at this moment they start thinking in these lines, so I'm sure that the timelines that you are saying is by 2035, maybe you can still bring it down on it.
Thank you so much. I have to stop also here because there's another event that is already, I have to be there. They are waiting for me.
Sir, I think just one question, because one participant, she has raised her hand. So because I intervened, so they could not speak. So
Yeah,
please give them
please
the
go ahead. The
opportunity.
last question. Yeah,
Rashmi,
thank you.
you may ask.
Okay. First of all, sir, thank you so much for such an informative session. I have a question that a lot is invested in extracting nuclear fusion energy. So would this energy will be cost efficient for a developing nation like India?
So energy costs are independent of country. And obviously the early stage when you develop something, the costs are higher. And as you start to do it at a larger scale, the costs come down. So we believe that it will be cost effective. Otherwise commercial use will not be there. But first we have to realize it technologically, and then the economic part will also come in. So obviously economic role is going to be there. And the reason why, like I mentioned about medical isotope which we are working on, is that $3 billion it will cost to set it up. But every year I get $5 billion return. So you see, there's an economic factor that is coming in because it's so costly. So energy has many factors in addition to what you see, direct cost and indirect cost that we're suffering from the global warming, everything that is happening. So obviously it has to be economic, otherwise it will not be commercially successful. So I'll stop at this point. Thank you so much.
Thank you, sir, for this lively interactive session.
And you can connect to my blog is there. You can read through those and you can connect to me. I'm very accessible. So thank you so much.
Yes, sir. Thank you, sir, once again. I would like to request everyone to fill the feedback form, the link of which has been provided in the chat box.
Padu, what you can do is there are a few more questions in the chat box. So maybe you can share these questions with sir, and maybe he would, because he already said that he is accessible. So maybe he would give answers to these questions also. So
Yes.
while sending a thank you letter to him, please send these questions.
Oh, okay, ma'am, sure.
So, Parul, can I take over from here?
Ma'am, actually, I have to request for a group photograph with the sir.
But sir has already left.
Okay, okay.
He was in a rush. That is why, we couldn't accommodate that request. Before we move on to the much awaited student prize distribution session, we would like to remind you that the annual conference Equinox is organized under the Aegis of Vantage Journal of Thematic Analysis. This is a peer-reviewed multidisciplinary journal that publishes original research article, reviews, opinions, perspectives, to name a few. Every issue of this journal revolves around a particular theme and critically discusses the theme from vantage point of various disciplines. Till now, we have